one. Okay. Okay. All right, we are recording. I want to make sure that was working. And before we get started today, let's go from current slide. Before we get started today, let's talk about how the term's going to wind up. Okay? We have class today. We have class Thursday. Next Tuesday is the final exam. Okay? So first question I have, and I wish I had a full room here to ask this. We've got at least one more here. Daniel's here. And Dakota's here. All right. Anyone else coming since they're called up? Okay. How many have done the student course evaluations? All right. Please get them done, folks. Please get them done. I'll probably ask that every time someone new comes in because they're really pressing this term. And actually from now on, probably. All right. Second thing, and this is a completely separate issue. What's 1 week from today? Okay, final exam. That's right. Yes, it's time to vote for this U.S. Senate seat. And on that, let me say this. I know it's our final exam, but I'm here until 8 o'clock on Tuesday evenings. I can't vote after work. I've got to vote on my way into work, and that may mean, if there's a bigger crowd at the polls, I hope there will be, that I might be a little late getting here. So don't panic. I will get here. I'll give you all the time you need to work on the test. So don't panic if I'm not here right at 8 o'clock. I'll try to be here. I'll do my best. I'm going to try to get to the polls early, but it could be a big crowd there. I hope there will be. Okay? So, but that'll be next Tuesday. But you're right. Final exam and voting for the U.S. Senate seat. Okay. Next. I do have an awfully big stack of papers here. And the reason I have it is that, okay, let me start with this. Research papers. Fewer than half of you have turned in the research paper. Folks, I need those. Thursday's the last day you can get it in without losing points. I'd rather have it today. I'd rather have it tomorrow, but I will take it on Thursday too without losing points. Now, I will take it after that, but you'll start losing points after Thursday. So please get me your research paper. Okay, quiz 1. Still have a quiz 1 out, right? Okay, please get that into me so I can return those papers. You're not the only one. There's at least 2 others who have not turned in quiz 1. Huh? You'll get it. Okay, I've got to get it, okay. Because if you haven't turned in a quiz, I've got to give you a 0 on it. So please turn in a quiz with something. Also, test, if you haven't done or finished one of the tests, please get those done. Otherwise, you get either the 0 or the partial score. Neither one of them is going to have to grade very much, okay? So please get those tests completed. Quiz 2, there's still people who haven't turned that in either, so and haven't finished test 2. So please get that done before Thursday, because guess what? Thursday morning, I return every one of those quizzes and tests. If you haven't turned it in, too late after that. So please, this is Asata, right?
After what?
Huh?
After what? Too late after.
I'm sorry?
Is it too late after?
It's too late after Thursday morning. I'm returning the papers to you on Thursday morning. That means I've got to have them in by Thursday morning. Anything after Thursday morning, the papers are out there. I can't accept your work. So you've got to get it done today, tomorrow, or basically, if you want to work on it during class on Thursday, not a good idea, but you can. But please get those things in because I cannot accept them after Thursday.
You cannot accept quizzes and sheets after that.
Quizzes or tests, right, because I'm returning those to everybody else. So the correct answers are going to be out there. And I can't receive work after that. Okay, Trey is here. So please get it in, folks. Get in your research paper, your quizzes, and your tests. Those will be returned first thing Thursday morning. Okay? Now, let me just go over this too. My office hours this week are today and Thursday, 1:15 to 3:15 here on this campus. Tomorrow, Wednesday, 3:15 to 5:15 here on this campus. Friday, 7:45 to 11:45 on the Birmingham campus. Okay? Now, next week, during finals, that's a little iffier. You know, your final schedule is not the same as class schedule. Somewhat similar, but not the same. For instance, Monday, during finals week, I'm offering that class a chance for another review session. So I'll be in this classroom conducting a review session from 8 o'clock until 9:50. That's Monday morning. Anytime after that, I'll be giving the test on to that class. It may be Monday, Tuesday, Wednesday, or Thursday. I give them the option of when they want to come take it. Okay, so I'll get back to that in just a minute. Then Tuesday, this class has its final, 8 to 9:50. You have an hour and 50 minutes, not an hour and 15 minutes. Okay, so almost 2 hours to do it. Again, for those who came in late, next Tuesday is election day. It's a strange time for an election day, but I have to vote before I come in because I get off at 8 o'clock. Polls will be closed then. So I have to vote on my way in, and they don't open until 7. I'm going to try to be there before 7, standing in line to vote just as quickly as I can. I just don't know how long the line will be or how fast I'll be set up ready to take the vote. So hopefully I'll get here by 8 o'clock. But if not, don't panic. I'll be here. I'll give you any extra time you might need. All right. Tuesday afternoon of finals week, I have a mini-term class, so I'm actually teaching that Tuesday afternoon from 3:15 to supposedly 7:45. I doubt if we'll go that late, but that's a regular class day for second mini-term. So I'll be up here in the classroom then. Then Wednesday, I may be giving the final, like I said, for that Monday class that I gave them an extra problem review session. And then on Thursday is when I give the final for that mini-term class, so 3:15 to, but that I know will not take long because the final exam in that class is fairly short, they'll be wanting to get out of there in a hurry. So I won't be up here long. So, except for Monday, 8 o'clock, Tuesday, 8 o'clock, Tuesday, 3:15, and Thursday around 3:15, except for those times, I could be in my office, I could be in this classroom, or I could be any room in between, because people do come by to take, makeup work and stuff like that. So I usually find the closest classroom to my office, and that's where we'll set up and go. So if any of you, need to come back and finish something, if I get here late, you don't have time to finish your final, anytime, find me in my office or any room in between my office and here. There's got to be a classroom open between here and there. This one's just about always open, but I like to get closer to my office for makeup tests so I can hear the phone and go back and forth more easily. So does that make sense? Any questions? Okay. So again, a few more people have come in since I asked this question. How many have done the student course evaluations? Okay, not everybody. Please get those done. Please get the student course evaluations done. All right. Any questions before we get started today? Yes. Say that again. 8 on Tuesday. Yeah. And if you did miss if you haven't turned in that last quiz, I need that in. And if you haven't done the last test, well, either quiz or either test, those have to be done before Tuesday morning. Thursday morning, Thursday morning. So get it done today, get it done tomorrow, or before class on Thursday. Okay. What's there?
Like on Tuesday is when we're taking our final, right?
Yes.
And on Thursday, what are we doing?
What? This week or next week?
Next week.
Next week, nothing. It's only if you need to come back and make something up. I mean, to finish the final or something like that, like if you got sick or something, yeah, you could. But I mean, you don't have to wait till Thursday. But there is no class on Thursday. Finals week is completely separate, except for second mini-term classes. They still have class the first day and then have the final the second day. So that's one of the weird things about mini-terms. All right. Any other questions? All right. We were going to do example 3. Let me get my pen adjusted. Yesterday, for some reason, you see, I can't do the black ink here because that's the symbol that stops the recording. That's how it's always been. Except yesterday, it was over here, and I could use the black ink. Today, it's back over there. I don't know why it changed. Maybe it was, I don't know. Okay, so I'll have to use the dark here. Okay. Example 3. On the same coordinate plane, so let me kind of draw that in. Okay. Okay, there's my coordinate plane. Sketch the graph of each function. And the first of these is capital F of x. You can name it anything you want to. Capital is equal to 2 to the minus x. Okay? Now, give me some x's. Let me take off a few points here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I won't need that many. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And we could go down a couple, but we won't need those either. So give me an x. I feel like a cheerleader. Give me an x. 3. Okay. Say 3. All right. 2 to the minus 3 would be what? So f of 3 would be 2 to the minus 3. What is that? Say again? A little louder? Negative 16. Not quite. What a negative exponent means, you go downstairs. So that's the same as 1 over 2 cubed. Remember? What's 2 cubed? 1 over 8. Perfect. So in x equals 3, your y or your is 1 over 8. Somewhere about down there. Give me another x. 5. Ooh, I like big numbers. Alpha 5 will be 2 to the minus 5. And what does that mean? 1 over 32. Okay, so that's way down here. Okay, even closer to the x-axis. All right, I think I see what's happening for large x's. Let's get a little bit smaller x's. 1. Okay, what's alpha of 1? 1 over 2. Exactly. Okay, so alpha of 1 is 1/2. Okay, give me another x. Phone's here. Wait just a second. Find my way across the grade book. Okay, what do you say?
2.
2? Y'all like to go back to the big ones, don't you? What's alpha of 2? 1 over 4. Very good. Right there. See the pattern? It seems to be working, so let's go a little to the left. We've done to the right. Stand up, sit down. No, we won't do that one. Okay. Say again? 0. Okay, what's alpha of 0? Is what? 2 to the minus 0. And what's the number to the 0th power? 1. Okay, when x is 0, y is 1. I think I see a pattern coming here. Okay. Give me another one. Negative 1. F of negative 1 will be 2 to the minus a minus 1. What's that? 2. Okay, so when it's negative 1, you're 2. Okay? Negative 2 will be what? 4. Negative 3 would be 8. 5, 6, 7, 8. Who do we appreciate? Okay, here we go. There. And 4 would be 16. That's going to be off scale. Here is the graph of the exponential function when you have a negative exponent. Positive exponent, if you remember what we did before, always went up. Exponential growth. This is exponential decay, getting smaller. What are some features of this that you can tell? Number 1, what's its domain? All real numbers, okay? What's its range? Courtney, wait just a second. Okay. Say that again. You probably said it right. I was just, what did you say? Range? From, okay, domain is all real numbers. You can put any x in here and you still get a y. Okay, what's your range? You may have said it right, I couldn't hear. 0 to positive infinity, exactly. Is the 0 included or not? Not included. Parentheses by the 0, not a bracket. Parentheses. Because it never, ever, ever, ever reaches 0. It gets closer, 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 but it never reaches 0. Okay? Is it increasing, decreasing? Decreasing always, okay? Whereas exponential growth is increasing always, okay? How about x-intercept? None, because it never reaches the x-axis. How about y-intercept? Yes, 0, 1. In fact, every exponential function, whether it's positive or negative, is going to go through 1. Unless, of course, you have a vertical or horizontal shift or something like that, then it wouldn't. But the others went through 1 going up, these go through 1 coming down. All right, good deal. See, is there any other questions I should be asking about that? We'll get to those later. Okay? Let's now do the B part, which is g of x. Okay? What color you want g of x to be? Yellow. Okay. We'll see if we can see yellow. So your g of x is going to be 4 to the minus x. Can y'all see that? All right. Good luck with that. Okay. Give me an x. 0. What would g of 0 be? 1 again. Perfect. Okay. Give me another x. Negative 2. Okay. G of negative 2 would be 4 to the minus a minus 2. What would that be? 16. Already off scale. Okay. So 2 would be off scale already. Okay. So give me one not quite as far as negative 2. Negative 1. What's g of negative 1? This would be 16. Yes, that would be 4. Okay? At negative 1, you're up to 4 right there. Okay? Now let's go a little to the right. Okay, g of 1 would be 4 to the minus 1, which is 1 over what? 4, exactly. So that would be down here. Okay? How about negative 2? 2. G of 2 would be 4 to the minus 2, which would be 1 over 16, way down there. Here's what it looks like, folks. It's starting from way up here, coming down, going through 1 again, and then approaching 0 even faster than the other one did, but never getting there. Okay? So those are the plot of the two graphs on the same curve. Make sense? Same axis. Make sense? All right. There is a checkpoint. If you need to do it, please do it. Okay? Now, few things that we note, and we've already asked this question before, but this is on the next page. What's the domain of both of those functions? All real numbers, range? 0 to infinity, with 0 being not included, parentheses, okay? X-intercept? None. Y-intercept? 0, 1. Perfect. Both of those functions, increasing or decreasing? Decreasing. Perfect. Okay? Is there a vertical asymptote? No. It just keeps on coming up here. There's no vertical asymptote. Is there a horizontal asymptote? What? Yes. Y equals 0. Always do a Y equals. Okay? Is it a continuous function? Yes. No holes, no gaps, no breaks, nothing. Okay? Always a continuous function. Okay? So, we've already done example 2, so we'll go to this. So here's what we were looking at. Example 2 was an expression like this, a to the x, where x is a positive number. And then we said the domain was all real numbers, range 0 to infinity, with the parentheses in front of 0. Y-intercept is always 0, 1, unless you have a shift or something like that. A to the x is always increasing. That's exponential growth. The x-axis is a horizontal asymptote for negative x's anyway, not for positive x's, but for negative x's. And it's always a continuous function. Okay? This is when your a is greater than 1. Okay? And generally, we don't ever let a be negative, and we don't let a be 0 or 1. But it can be greater than 1. All right. Any questions on that? Actually, if a was between 0 and 1, that means it's a fractional form, and that would then be like your exponential decay, because then you would have a small number you're raising to the big powers, and it would get smaller and smaller and smaller, and it would look like this, okay? So, all right, so the graph of y is equal to negative x as long as a is greater than 1. Domain, again, is all real numbers, range 0 to infinity, not counting 0. X-intercept none, y-intercept 0, 1. This is a decreasing function. We call that exponential decay. Again, the x is a horizontal asymptote for positive x's, not for negative, but for positive. And it's a smooth and continuous function. Notice that the graph of an exponential function is always increasing or always decreasing, never has a change. Never. Never what do we call that? Maximum, yeah, an extremum. Always increasing or always decreasing. All right. As a result, the graphs, if they're always increasing or always decreasing, they always pass the horizontal line test, right? Remember horizontal line test? What does that signify? One-to-one functions. Very good. So you can use the one-to-one property to solve some simple exponential equations. So again, here's what restrictions are on your A. A is the base now. A has to be greater than 0. We never have negative bases. Greater than 0. But we also don't let it equal 1. So it could be a positive number between 0 and 1, but it can't be 0, it can't be 1. And then it could be any positive number past 1. Okay? So as long as it's neither 0 or 1, always positive. If a to the x is the same as a to the y, guess what? X and y have to be, if and only if x is equal to y. That's one of the one-to-one properties. Because you only have one x for any one y and one y for any one x. Okay. Whoa! They are skipping example 4, example 5. So let's do example 4 and 5. Goodness gracious. All right, we'll put them back here. Wrong one. Okay. All right. Whoa, let's can the yellow. Okay, it's pretty, but we'll go back to dark. Okay. What if you had this equation? 9 is equal 3 to the x plus 1. 9 is equal to 3 to the x plus 1. And we want to solve for x. How in the world could we do that? Mystery, huh? Well, if you review what we just stated, we said the one-to-one property said if you have the same base, different exponents, and they're equal to each other, those exponents have to be the same. So basically, you got to get the same base. What's your base here? 3. What needs? Can you write 9 with the base 3? What? Second? 3 squared, you got it. 3 squared is equal to 3 to the x plus 1. Now it's pretty easy. What would you do? You say 2 is equal to x plus 1 and solve for x. And what would x have to be? Subtract 1 from both sides and you have x is equal to 1. Perfect. Okay? Because 3 squared, if that's a 2, this has to be 1 plus 1 to make it 2. Perfect. Okay? How about this one? 1/2 to the x is equal to 8. How would we do that? All right. Okay. Say that again. Okay. She said make the 8 a 2. 8 is 2 to the third. Okay? That's what 8 is. Okay. We want it to be a 1/2, so move it downstairs, and you have to make it 1/2 to the negative 3. So yes, you are very, very close to it there, which is the same as, because 1 is 1, that's 1/2 to the negative 3. There, you've done it. Now what can you say? X equals negative 3. There it is. You see it? X equals negative 3. All right? Because if you did 1/2 to the negative 3, that would be 2 to the third, and that is indeed 8. So there's several ways you can approach that. All right. This isn't normally how we do one-to-one functions, but if you have it set up for you, it's pretty easy to do that way. Okay? Now, like I said before, occasionally you can have transformations or, shifts and that kind of stuff. So when you do, then you're not going to go through 0, 1, but you'll go through something similar to it. So let's do example 5. Okay? Now, if you notice in your book, it says see larsonprecalculus.com for an interactive version of this type of an example. They are doing this right out front. They usually wait until they do the checkpoint. They do a checkpoint, but this is sort of a new concept. They didn't do it on the slides. So he's encouraging you to use larsonprecalculus.com. And frankly, folks, I think I said this early in the term, I do not like this publisher. I think these books are too expensive, and they are, I just don't care for the publisher, okay? I really don't care for WebAssign either. But this author is just about the best author I've ever seen. He has all these free interactive guides. He has calctrack.com, calcview.com, and larsonprecalculus.com. All these things for you to use without going through WebAssign, without buying anything else. You buy the book, you get access to that. In fact, You don't even have to buy the book to have access to that. So please take advantage of him. He must be a pretty good guy. I've never met him, but you know, his is the. I've never seen anyone else do this with a text. All right. So describe the transformations of the graph of, now original graph is f of x is equal to 3 to the x. Okay? So let's go on and draw that one. Okay? And unfortunately, I'm going to have to do it here. So what I'm going to do here, because that line is confusing, I'm going to take this line off. And what I think I'll, excuse me. Y'all awake yet? Okay, good. All right. Okay. Okay. Let's graph that function there. Give me a few points. Well, let me tick off a few. 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 4, 5, 6, 7, 8. Positive 1, 2, 3, 4, 5, 6. Okay. Give me a few points. Give me an x. Second? 0. What's your alpha of 0? 1. Excellent. Give me another x. 1. What's alpha of 1? 3. Very good. Okay. Give me another x. Negative 1. What's your alpha of negative 1? 1 over 3. Excellent. Okay. See the pattern? I'm going to go on and draw it in. Okay. Alpha of 2 would be 9. Alpha of negative 2 would be 1/9. Okay. Pretty ugly picture. Okay. Now, let's do, give me a color. Say again? Purple. Okay. We're going to do G of x is equal to 3 to the x plus 1. What do you reckon that one's going to be? Say that one more time. You may have been right. I can't hear. Sorry. Sorry. What do you reckon happens here to G of x? What are you changing in this? You're adding something to the x. So what's that going to be doing? Yes, it's a horizontal something or another. Okay, we call it a shift. Which way? To the left. To the left. Remember, anything to do with x is sort of backwards, so it's going to be to the left. So move this one to the left. Move this one, that should be one to the left there. Move this one to the left here. There it is. Okay, it's coming like this. Oops, I missed it. Missed it pretty badly. There it goes, something like that. Okay. Let me get rid of that one too much. Okay. All right. Give me another color. Orange. Orange, you glad I chose orange? Okay. All right. This is going to be h of x is equal to 3 to the x minus 2. Now, that minus 2 is down here, not up there. What is this happening? What's happening here? Go back to your original, your f of x. Don't worry about g of x. What's happening to it? Say again? Okay, no. Right or left would be something changed to the x. Remember, this is not with the x. This is down here. It's with the f of x. So it's a down 2. Okay, so every one of these points goes down 2. 1, 2, 1, 2. It would be somewhere about like that. This one goes down 2 to somewhere about like that. Every one of them goes down. Now your new horizontal asymptote is y is equal to 2, not y is equal to 0. So it's coming across like this and going up like this, just like this. A shift downward, okay? Yes, okay. I couldn't see my mark. I went right through it. That's surprising. All right, give me another color. Green. Green, green, it's green, they say, on the far side of the hill. K of x, y'all don't remember the old, never mind, is equal to -3 to the x. What have we done to, again, go back to our original f of x. What have we done to it? We flipped it across the x-axis, yeah, because it's negating the y's. So this one will flip down here, this one will flip down there, this one will flip down here, okay? So it is going along like this and go like that. Exactly a mirror image across the x-axis of your f of x. Perfect, we all are good. Let's do the J of x. What color you want J to be? Yellow. Okay, y'all won't leave yellow alone, will you? Okay? All right. J of x, if you can read it, is equal to 3 to the minus x. Okay, how does that compare to what F was? F and J. What have you done? That's you reflecting across the y-axis. You're absolutely right. So this stays exactly where it was. This now is over here. This one is over here. And your function is doing like that. Just a reflection across the x-axis because you negated it. Across the y-axis because you negated the x. Very good. Y'all are good at that. Really good. They do have some checkpoints there, so please do those. And again, audio-video solutions for in both English and Spanish are at larsonprecalculus.com. All right, now let's move on to natural base, E. Any of you know much about E? Okay. If I said, what's the base of our number system, what would most people say? Say again? What's the base of our number system? 10. Is everything based on 10? Your 10 fingers, 10 toes? I think that's why our base is 10. That's how we normally think of it, okay? Because once you get to 10, you move up one, okay? 1, 2, 3, 4, you then move up one. And then you get 10 tens, you got 100. 10 hundreds, you got 1,000. Everything's based on 10. Okay? However, that's a practical base, basically, because of our fingers and toes, probably. That's how we learn to count, right? Some of us still never. Okay. So, in calculus, however, and this is pre-calculus, we have found that the natural base of our number system is not 10. It's this weird little irrational number called E. There's many other irrational numbers. Can anyone think of a very famous irrational number? Pi, exactly. What does it mean to be irrational? Nothing to do with gender, by the way, okay? What does it mean to be irrational? Huh?
Just different from us.
Okay. Well, rational means ratio of two integers, right? Irrational means you cannot express a number as a ratio of two integers. Pi you cannot, E you cannot, square root of 2 you cannot, square root of 3 you cannot, square root of 5 you cannot. You have lots of irrational numbers. Cannot be expressed as a ratio of two integers. Okay? Another way to express that, if it can be expressed as a ratio of two integers, then it can be written in a fractional form where that I'm sorry, a decimal form. A fractional form is a ratio of two integers. Okay, that's given. But in a decimal form, the decimals are either going to terminate, like 0.75, they stop, or 0.6666666, they just keep repeating some digit, or some series of digits, like 0.73223223232. It starts repeating at some point and never changes. E and pi and square root of 2 never repeat any pattern whatsoever. Ever. Okay. So here it is, an irrational number. And what's amazing about that? It's the natural base for our number system. Okay? Especially in the calculus sense. Okay? Here it is, the first few digits of it. 2.718281828. Oh, it looks like it's repeating 1828. No, it's not. Okay? They just stopped printing right there. If you went one more digit, you see the pattern is busted. Okay? It's called the natural base of our number system. Now, if you did the graph of that, we did the graph earlier of f of x is equal to 2 to the x. That would be, have 0, 1, 1, 2, 2, 4, negative 1, 1 half. Well, this is something a little bit off from that, not far off. 3 would be even closer. 1, 3, okay? Negative 1, 1/3, okay? It would be a little bit different from that. This is in between 2 to the x and 3 to the x, okay? That's just one way to look at it. Closer to 3 to the x. But it's an irrational number, e to the x, okay? It's called the natural exponential function. There's its graph. It looks just like every other exponential graph with a positive base, and e is positive. It's exponential growth. Not as fast as 3 to the x, a little bit faster than 2 to the x, but it's right in there. Okay? And here's Jalen. All right. Now, and I said I was going to say this every time someone new came in, so let me say it again. Please remember to do the student course evaluations. All right, good deal. Excellent. Okay. And have to have every quiz and every test finished before Thursday. So get it done today, tomorrow, or before class, or by class on Thursday. Okay? So here is a new base, E. Okay? It says, be sure you see that for the exponential function, f of x equal e to the x, e is some constant, and they stop at that. I wish they'd have done just a few more digits or something, where x is the variable. Just like all our exponential functions. X is the variable, e is a number. It's the base. Okay? We treat it like it's a function, but it's really just a number. Okay? So it says use a calculator. And folks, I think I said this before, but if I didn't, let me say it again. Please bring your calculators to the final exam, because I don't have but I think one functioning calculator anymore, and it's pretty sorry. All mine, the batteries have died, or people have walked off with them, or whatever. And so I can't provide calculators. You will need them on the final. So please bring your own calculator and know how to use it. Okay, get familiar with it. Okay, so do this. Use a calculator to evaluate the function f of x equal e to the x at each of the following. X equal minus 2. So I'm going to punch that in and see what you get. F of x equal e to the minus 2. Should be something a little bit greater than 1/9. Anyone got it yet? Point. Yes, that sounds pretty reasonable. 0.125, is that what you said? Huh?
0.135.
Okay. So, let me get back to dark again. Okay. E to the minus 2 is approximately 0.12 what? 135. Okay, good. How about e to the minus 1? What would that be? That would be a 0.327?
67.
Huh?
67.
67. Okay. All right. How about e to the 0.25? What would that be?
1.284.
1.284. Very good. Okay. How about e to the negative 0.3? 0.74. Okay. Now, what are a few things you notice about this? They're all positive. Just like every exponential function, it's never negative. The domain, all real numbers, but the range is from 0 to positive infinity, not counting 0. Non-negative, well, no, it's positive numbers, okay? And if you have a e to a minus number, it's less than 1. If it's you can talk about all sorts of things. E to the 0 would be 1. Anything greater than 0 would be greater than 1. And you see that e to the 0.25 is just a little bit greater than 1. Anything less is going to be less than 1. Okay, good deal. And they're one-to-one functions, right? They're strictly increasing, unless it's e to the minus something would be strictly decreasing. Okay. Let's see how the book did. 0.135, 0.637, 1.284, very good, and 0.2, yeah, 0.74. Excellent. So let's do, oh wait. Wait, that's the wrong button. Whoa. All right. Oh, they show how to do it just like you did. You got it right. 0.135, 0.367, 1.284, and 0.74. Okay. Now, they're skipping example 7. So, let's graph some natural exponential functions. Let's go back to this one. Okay? Let's graph this one. All right. Okay, there's our graph. And we're going to start with f of x is equal to 2 times e to the 0.24x. 2e to the 0.24x. All right. Let me tick off a few points. Won't need that many. Okay. Give me an x. 0. What's alpha of 0? Okay, this is a little trickier. E to the 0 is 1, but then you got 2 times that. So that's a 2. So it's not only the shifts, it's also the stretches that will change that a little bit. Okay, give me another x. Negative 1. So that would be 2 times e to the negative 0.24. So punch that in your calculator and see what you get. That would be f of minus 1 would be 2 times e to the minus 0.24. What you get? 1.57. So negative 1 would be 1.57, something about like that. Okay? Give me another x. Another x. Alpha of negative 2. That would be 2 times e to the negative 0.48. Right? Put that in your pot and cook it. Okay? You want to get an answer yet? By the way, cell phones, most cell phones will have these keys on them too. You may have to turn your cell phone landscape to get it to do, but you should be able to do it. What you get? Anybody? 1.23. 1.23. Something about like that, maybe. Okay? How about something to the right? Or you can go to the left. I don't care. Give me another x. F of 1. That would be 2e to the 0.24. And what would that be? $2.542, is that what you said? Okay. 1 would be 2.542, something about like that. Okay? Hopefully we see the pattern coming. You could do a few more if you wanted to, but it's going to be something like this. Okay. Now, because it's a small exponent here, okay, it's going to be going up more slowly than if that was just e to the x. Okay? It's 0.24x. So it's coming down more gradually here and going up more gradually there. Okay? So that's what, goodness, where is it? Example 7, A looks like. Let's do the G. I need another color. Any color? Blue. Okay, we haven't done blue. You like light or dark? Dark. Okay, dark blue. Okay. Let's do G of x is equal to 1/2 e to the negative 0.58x. Where did that come from? Okay. 1/2 e to the negative 0.58x. Did I write it right? I think so. Give me an x. 1. So G of 1 would then be 1/2 e to the negative 0.58. Punch that in your calculator and see what you get. Or throw your calculator around. Huh? Say again? 0.89. There's this is 1. 0.89 would be something about there. Something just less than 1. Okay? Give me another x. G of 0 would be 1/2 e to the minus 0. 0 was just 0. Okay? What would that be? What would that be? Okay. You say 0.5, okay. I need you to go back and revisit 1. That doesn't seem right. Did you say 0.89 or 0.289? The one we did before. This is, as you said, 0.5. Okay? But that previous one you gave me I don't think is right, or I misunderstood because my hearing's not good. 1/2 e to the minus 0.58. What did you say it was? Help me, help me. Someone help. Y'all got the calculators? 0.28, that's what, okay. I misunderstood. I thought you said 0.8. 0.28 is just over a quarter. So somewhere down in there. Okay. Give me another x. Say again? I can't hear. 1? Didn't we just do 1? Huh? 2. Okay. G of 2 would then be 1/2 e to the negative 1.19. Right? 0.152. Okay, that would be even smaller down here. Okay, I see what's happening if you go to the left. What happens if you go, to go to the right, what happens if you go to the left? Like -1. G of -1 would be 1/2 e to the 0.58. What you get there? .393? 0.893. Okay. That's better. Something like that. So here's what's happening now. I'm going to have to curtail it because we're running out of time, but it's going up pretty slowly like that. It's exponential decay because you have a negative exponent. Okay? But it's a fractional. Okay, the 1/2 is a vertical shrink. Okay? So that shrunk things this way. It would have been a 1, but it shrunk that way. The other was a vertical stretch because it was a 2. And then the 0.58 is a horizontal stretch, okay? But then negative, yeah, so flip it back. So yeah, that's what it looks like. And you see in your book, they're not far off either. Make sense? All right. So there's how you graph natural exponential functions. Plug them in, plug them in. They do a lot more points than we did, but you get the general idea. All right. Now let's move to applications. One of the most familiar applications of exponential growth is an investment earning continuously compounded interest. That's how we like to earn that interest. The trouble is it's such small interest today, it grows so slowly. Okay. But the formula for interest compounded in times a year, like if this were once a year, this would be A, your amount at the end of the year is your principal at the beginning of the year, times 1 plus, and if it's R, what's the interest rate now? Anyone know?
I think it's 0.15.
Yes, awfully small. 0.15. I mean, that's pathetic. 0.15, if it's only done once a year, then that would be 1 plus 0.15, so that would be 1.15. So whatever, raised to the how many years, okay? Because the end would be 1. If it's twice a year, semi-annually, then it's that same interest rate divided by 2, but then your exponent is increased by 2, is double the 2. 4 times a year quarterly, then yeah, your rate is divided by 4, but you raise 4 times, so your exponent is even greater, okay? And you keep on going like that. Daily would be over 365, and 365 up there. So, believe me, the amount doesn't change much, but it does get better every time you compound. And that formula, A is the balance in the account, that's the amount, P is the principal, the original deposit, and R is the annual interest rate in decimal form, and it's the number of compounding per year, and T is the time in years. Okay? Now, that's a fairly hairy-looking formula, but it's an exponential formula because your time is your variable here, and it's raised to an exponent. Okay? So it is an exponential equation. Okay? But using the exponential functions, you can develop this formula showing how it leads to continuous compounding. Suppose you invest the principal P at an annual interest rate R, compounded only once a year, If the interest is added to the principal at the end of the year, then the new balance, P1, is your original principal plus the interest that you earned. That's your, after 1 year, that would be your new principal. And then you do that again and again and again. Every time is P times 1 plus R. Okay? So after R years, I'm sorry, after 7 years, P7 is going from there. Okay. So, this is what I was just going to say. The pattern of multiplying the previous principal by R plus 1 plus R repeats each successive year. So the first year, the principal is your principal. Okay? 0 year, that's all you had. 1 year later, it's principal plus 1 year's interest. So 1 plus R. P2 would be P1 times this P1 times 1 plus R. So P1 is P times 1 plus R. 1 plus R times 1 plus R is 1 plus R squared. So you see P7 then would be P, your original principal, times 1 plus R to the 7th power. Now for very small r's, that is increasing, and it, over time will increase, but it's very, very slowly. Okay? For generous interest rates, none of you were probably born back when we had interest rates that were in the close to double digits. It really, it makes money. Of course, if the interest rates you were earning, interest rates you were paying were even greater. But the strange thing is, even though today's interest rate, you said 0.15 or something like that, okay? Guess what you're paying on your credit cards now? About 24%. You earn 0.1%, 0.15%. They're still charging what they did back when the interest rates were 10%. Yay! You know what phrase that goes with that? The house always wins. The bank always wins. Never mind. I'll go into that. Okay. All right. Now, to accommodate more frequent, that's quarterly, monthly, daily compounding rates of interest, let n be the number of compounding per year. This is the same thing we had before. While they're coming back to it, I'm not sure. Then the rate compounded is R over n, and the account balance after T ends. This is exactly the same formula we had before. Amount is principal times 1 plus R over n raised to the nt. Okay? When you let the number of compoundings n increase without bound, that's what we call continuous compounding. Okay? And that produces a sort of interesting kind of problem here. The formula for n compounding per year, let m equal n over r. Now, they really are mixing this up pretty badly, okay? So, the m is n over r. Remember, we had r over n here, so that's 1 over m. Our n was n times r, so that just becomes 1 over m. So, this is what's being compounded, okay? 1p times 1 plus 1 over m raised to the m times RT. Okay? Now, that's from your properties of exponents. I don't want to get bogged down here. I want to get to the cut to the chase here. As m increases without bound, that's as m's going to infinity, this shows what this produces. 1 plus 1 over m raised to the m power. Okay? If that m is just 1, that'd be 1 plus 1 over 1, which is 1 plus 1 is 2. 2 to the 1 is 2. If that were 10, you'd be 1 plus 1 over 10, which is 1.1 raised to the 10th. Plug that in the calculator, you see this. 100, 1,000, 10,000, 100,000, 10 million, go on up right. Guess what this is getting closer and closer to? That's why it's the natural base of our number system, because this pattern keeps repeating itself, and that as this goes to infinity, this is going to that funny little number, irrational number, E. Go to 100 million, you'll be even closer to E. Keep on going. So, what you can do is change your formula to be A is equal to P, E to the RT. Okay? This makes it so much simpler than that other formula that we were using. Why all banks don't use continuous, maybe they do these days, I don't know. But here's the formula for compound interest. If it's repeated n times a year, it's this formula. It's okay, pretty hairy, but look how simple it becomes if it's continuous compound. A is equal to P e to the RT. Just that. It's very pert, isn't it? No. Okay. Okay. All right. So P e to the RT. Now, do we have time? Let's try it real quickly. You invest $12,000 in an annual interest rate of 3%. Dream on, baby. Okay, that's a long time since we've seen 3%. Does this new book have that too? Yeah, they say 3%. They didn't update that, did they? Okay. Find the balance after 5 years where the interest is compounded. Let's try it at least quarterly. Okay. What was that formula? Oh, let me go back to a darker color. A is equal to P times, what was that formula? 1, say again, plus R, and what's your N if it's quarterly? 4 raised to the 4 times 5. Okay? And your interest rate here, so your principal was $12,000. Okay, $12,000. Oh, I wish that were true. Okay. 1 plus, and your interest rate was 3%, and 3% divided by 4 would be 0.03 over 4. Okay? Pretty small number raised to the 20. Okay? Can someone do that on your calculator and see what you get? You always put the interest rate as a decimal, 0.03. So that would be 12,000 times 1 plus, and that would be 0.0075. So 1.0075. Raise that to the 20th power. It equals what you get. Big finances these days, folks. 13,000. Say again? 900. And what? $34. We won't go into the pennies here. Okay? Hey, you earned almost $2,000 in those 5 years. Let's do it monthly. That would be A is equal to the same principal, 12,000, okay, times 1 plus, and now it's 0.03 divided by 12. Makes a much smaller number. But now it's 12 times 5. So that's going to be 60. So this is going to be, let me write it over here, 12,000 times 1 plus, and that's going to be, yuck, 0.0025, I think it is, right? Raised to the 60. Can someone do that for me quickly? 12,000 times 1.0025 raised to the 60th. Anyone do it? Well, I'm going to read it from the book. $13,939. You got an extra $5, okay, by compounding monthly rather than quarterly. Ooh, not too great. It's still got you a little more money. You can maybe buy a cup of coffee. Okay, how about this one's really easy. A is equal, remember what this one is? PERT. P e to the RT. That's all you have to do. Yes. I know. It's sad. I know. 12,000 e to the, and your r is 0.03 times 5, so that's 0.15, right? That's easy to plug in. What do you get there? 13,900 what? 42. Hey, another $3. Okay, I can buy half a cup of coffee. Okay, now, so you see, you do get a little bit better every time you increase better. Okay, we'll stop there, pick up next time with example 9. Okay, but before you go, homework exercises, any of the odds 7 through 11, 13 or 15 or both, 17 through 23, 25 or 27 or both, 29 to 30 or 31 or both, 33 or 35 or both, and stop there. We'll pick up from there.
Did you guys say this?
I think so. Let me see. Test 2. Yeah. Yeah. Sorry about that. Yeah, I'll go back and regrade that. Okay. Okay. And yeah.
You told us to turn in any work before you turn out the papers.
What's that?
You told us to turn in any work before you turn out the papers Thursday.
Okay. Yeah, I want you to get it done between now and Thursday morning. Okay. So do it today. Do it tomorrow. Get it done. Okay. Okay.
Which one did it do?
What's that?
Dakota.
Okay. You want to see your score?
Yeah, my test great.
Okay. Oh, wow.
Ooh.
Okay. Okay. Good. Laura. Okay. Sorry, I should be letting y'all of you see this. There you are. Okay. Okay. Yeah, believe so. Yeah. Yeah. I know you did quite well too, by the way. And fun. Yeah, good for 28. No, wait, I'm sorry, 93. Oh, wait, I haven't got you. I got your quiz graded, but not your test. 88. You're the next one I was grading. Sorry, I ran out of time last night.
Okay, I'm not happy with an 88.
Okay, good. It's good.
Did you get tomorrow?
Yeah. Yeah. Good. Quiz 98, test 90. Good deal. Y'all did well.
This section is the one that